Let's jump right in. Welcome to This Explainer, where we're revisiting the fascinating world of organic chemistry. You know, a lot of people look at this subject as just an endless, exhausting list of reactions you have to memorize. But actually, scratch that. It's really more like a highly logical system. Think of it like a giant Lego building set or even learning a new universal language. Once you get the hang of the foundational grammar and you understand the basic pieces, you can build literally anything. Okay, let's dive into this.
So, here's our syllabus for today. First up, we'll look at the magic of carbon. Then, drawing molecules. Third, we'll tackle naming rules. Fourth, reaction mechanisms. And finally, purifying and testing.
All right, part 1, the magic of carbon, the ultimate Lego brick.
It is honestly mind-blowing how a single element from the periodic table, just one, can be the entire foundation for so much variety in the known universe. And the secret to carbon's magic, it's a property called catenation. It's a great word, right? Catenation. It basically describes this unique, almost superpower-like ability of carbon atoms to bond with themselves. If you picture carbon atoms as the ultimate Lego bricks, they can literally snap together to form massive, long chains, complex branches, and even continuous loops or rings. And because they can do this, the number of combinations you can put together is practically infinite.
Now, what's really cool is how carbon's bonds actually dictate its physical, three-dimensional shape in space. Depending on how the carbon hybridizes, whether it's sp, sp2, or sp3, it creates totally different geometries. An sp3 carbon gives us this tetrahedral shape, an sp2 gives us a flat trigonal planar shape, and an sp carbon, it just lines up completely straight, totally linear. These aren't just abstract ideas on a chalkboard. This geometry is the literal physical foundation for all our molecular building blocks.
Moving on to Section 2, drawing molecules, spelling the words.
Okay, so now that we've got our carbon letters and we know their shapes, we have to know how to spell the words. And in chemistry, that means learning how to draw the structures. Now, drawing molecules has actually evolved quite a bit over time, mainly because chemists are, well, smartly lazy. At first, you have the complete formula, where you painstakingly draw out every single carbon and hydrogen atom. But honestly, who has the time for that with massive molecules? So we compress it down into a condensed formula. And finally, we arrive at the absolute gold standard, the bond line formula. Here, you're just sketching these super efficient zigzag lines. Every point or bend is a carbon atom, and we just assume the hydrogens are hanging out there. It is a massive time saver. And this brilliantly illustrates how we take those flat, smartly lazy 2D drawings and bring them to life in the real 3D world right on the paper. If you see a solid wedge, that means the bond is popping right off the page, coming directly toward you. A dashed line, that means it's pointing away, receding back into the background. It's such a simple trick, but it is an absolutely powerful way to visualize complex 3D architecture on a completely flat surface.
On to Section 3, the rules of naming, the grammar of IUPAC.
Think of this as the grammar of our carbon language. We use something called the IUPAC nomenclature system. This provides a universal set of rules so that a chemist in Tokyo and a chemist in London can talk about a molecule without any confusion. To climb this logical ladder, you really just need to follow 3 golden rules. First, find the longest continuous chain of carbon atoms. That is your root name. Second, number that chain from the end that gives any attached branches the lowest possible numbers. And third, when you write the whole thing out, just alphabetize the names of those branches. Follow those steps, and you can name virtually anything.
So, you might be wondering what happens when you have multiple functional groups fighting for attention on your molecule. Well, that's when you consult this ultimate hierarchy. For example, a carboxylic acid group, the COOH right at the top, outranks a sulfonic acid, which in turn outranks an alcohol group, the -OH. The highest ranking group is basically the boss. It gets to decide the molecule's core identity and its final suffix.
But before we move on from naming, I've got to share a fun little insider rule that textbook readers miss all the time. When you're alphabetizing those branch names we just talked about, prefixes like iso and neo actually count towards the alphabetical order. But the hyphenated ones, like sec and tert, they don't. No way, right? It's a tiny, quirky grammatical rule in organic chemistry, but it is absolutely vital for getting the name perfectly right.
All right, Section 4, reaction mechanisms, the action verbs.
If atoms are our letters and molecules are our words, then reactions, those are the action verbs. This is the moment where molecules interact, old bonds break, and incredible new structures are built. A reaction mechanism is defined as a sequential account describing details of electron movement, energetics during bond cleavage,
I really love this definition because it highlights that a chemical reaction isn't just some magic potion bubbling in a flask. It is a meticulously documented, step-by-step transfer of electrons that we can track perfectly.
Let's look at how this applies to breaking bonds, which chemists call cleavage. Think of breaking a bond like a molecular divorce. In homolytic cleavage, the divorce is completely amicable and equal. Each atom takes exactly one electron, which forms highly reactive things called free radicals. But in heterolytic cleavage, it is totally unequal. One atom takes both electrons, leaving the other high and dry. This creates charged ions, positively charged carbocations, and negatively charged carbon ions.
Now, once those charged species exist, they immediately start looking for new partners. And here we get two absolutely foundational terms, nucleophiles and electrophiles. If you want to understand them, just translate the names. A nucleophile is nucleus-loving. It's got extra electrons and is hunting for a positive charge. An electrophile is electron-loving. It's positive and desperately wants electrons. It's the ultimate chemical romance, really, opposites attracting to snap together and form a brand new bond.
And finally, Section 5, Purifying and Testing, Reading the Literature.
Okay, this is where we put on our detective hats. You've run your reaction, but now you're just staring at a flask full of gunk. How do you isolate your mystery compound and prove what you actually made? Well, first we have to clean up the mess. Chemists use a rapid-fire sequence of lab techniques based entirely on the physical properties of the molecules. We use sublimation if a solid can just poof directly into a gas. We use crystallization to let pure solids drop out of a solvent based on how well they dissolve. And we use fractional distillation to separate liquids by taking advantage of their unique, specific boiling points.
Once we've got a pure sample, we run tests to figure out exactly which elements are hiding inside our carbon framework. This is called qualitative analysis. We use highly specific chemical reactions that act basically like flare guns for different elements. For example, there's a specific test for sulfur, one for halogens, one for phosphorus, and a very famous one called the Dumas method that specifically identifies nitrogen.
Which actually brings us to this absolutely crucial number, 273. You see, the Dumas method isn't just about figuring out if nitrogen is there, it's about calculating the exact percentage of it. To pull that off, chemists rely on really strict mathematical formulas, using STP, that's standard temperature and pressure. And standard temperature? That is exactly 273 Kelvin. By locking in these standard conditions, the math beautifully reveals the precise composition of our molecule.
So, there you have it. We've covered the alphabet, the drawing techniques, the grammar, the action verbs, and the detective work of organic chemistry. With just a few simple, highly logical rules governing carbon, nature managed to build everything from the DNA in your cells to the plastic in the screen you are looking at right now. The rules are there, and the Lego bricks are just waiting. So my final question for you is, what will you build next? Thanks for joining me on this explainer, and keep exploring.